Okay, let's discuss how to obtain the Euler Lagrange equation. The Euler Lagrange equation is a fundamental equation in Lagrangian mechanics, used to find the path that minimizes the action of a system. The derivation starts with the principle of least action or principle of stationary action. This principle states that the actual path taken is the one where the action is minimized. Action is defined as the integral with respect to time of the Lagrangian. We can write this as S equals the integral from t1 to t2 of L of q of t, q dot of t, and t dt, where t1 and t2 are the initial and final times. Q, t, is the path, q dot of t is the time derivative of q, t, also called generalized velocity, and L is the Lagrangian. Our goal is to find the function q, t, that minimizes the action S. This is the calculus of variations. To solve it, consider a small variation in path backslash delta q of t. This represents small deviation from the actual path. We consider a new path, q of t plus epsilon eta of t, where epsilon is a small parameter and eta is an arbitrary function when t equals t1 and t equals t2, eta is 0. The action along the varied path is S of epsilon equals integral between t1 and t2 of L of q of t plus epsilon eta of t, q dot of t plus epsilon eta dot of t, and t dt. To find the minimum action, the action must be stationary. The first derivative of the action with respect to epsilon must equal 0. When epsilon equals 0, we can calculate ds slash d epsilon. This is equal to integral from t1 to t2 opening bracket, partial L over partial q, times partial q over partial epsilon, plus partial L over partial q dot, times partial q dot, over partial epsilon, close bracket dt. Partial q over partial epsilon is eta of t, and partial q dot over partial epsilon is eta dot of t. Substituting these now, we have ds slash d epsilon equals integral from t1 to t2 of opening bracket partial L partial q eta of t, and partial L partial q dot eta dot of t dt. Now part 2, we integrate by parts. Partial L partial q dot times eta dot of t dt equals partial L partial q dot times eta of t evaluated at the limits t1 to t2 minus the integral from t1 to t2 of d slash dt times partial L partial q dot eta of t dt, since eta of t1 equals eta of t2, which is 0, the first term disappears. Substituting, we are left with ds slash d epsilon is equal to integral from t1 to t2, opening bracket, partial L partial q minus d dt times partial L partial q dot, closing bracket, eta of t dt set ds slash d epsilon equal to 0 when epsilon equals 0. Since eta of t is arbitrary and can vary to always be 0, the bracket must be 0. Thus, we are left with the Euler Lagrange equation. In summary, the Euler Lagrange equation is derived by starting with action, considering a small path variation, calculating action derivative, performing by parts integration, setting derivate to 0. This provides a way to use Lagrangian to determine equation of motion.